Thanks a lot. Yeah, I would like to say thanks to the organizers for the opportunity to speak. I'm disappointed I couldn't be there in person, but I'm very happy to be able to be here online anyway. Right, so I want to talk today about how to study the homology of EN algebras, but I am not going to assume that you know what an EN algebra is. So let me start by explaining that very briefly. And I should say I'm trying to make this talk very accessible to people who are not algebraic topologists. So please feel free to stop me if anything is unclear or if I use words that you don't know. Okay, so the intuition you should keep in mind for an EN algebra is that an EN algebra is a space. For this talk, we'll say a space, but you can define EN algebras in more general categories. So it's a space that's equipped with a multiplication that's not strictly commutative, but that is commutative up to homotopy. Okay, so that's sort of some intuition you can keep in mind. And now let me say a little bit more rigorously what an EN algebra is. To do this, I'm going to define some spaces called DNK. If you know what this means, DNK is the kth arity space of the little n disks operad. Don't worry if you don't know what that means. Otherwise, you can take this to be just a configuration space. This is the space of ordered configurations of k points in Rn. And we'll use these spaces to define EN algebras. So an EN algebra then consists of a space X together with some extra structure, namely a bunch of maps going from the space DNK crossed with X to the K and landing in X. So I should have one of these maps for all K. And it's not quite so simple. They have to satisfy a bunch of extra conditions that take a while to write out. So rather than writing them out explicitly, let me say that it satisfies some associativity, equivariance, and unit axioms. So how should you think about this? These spaces DNK are basically parametrizing k-ary multiplications on X, because every time I have a configuration of points, I get one of these multiplications. And this associativity condition is saying something about how all of these different maps fit together for different k. So there is some coherence between them. The equivariance condition, maybe I can say something more about it. So there's an action of the kth symmetric group on X to the K, because I can just permute the factors of X. And there's also an action of the kth symmetric group on this configuration space, because I can just permute the labels of the points. So this equivariance condition is then requiring that this multiplication map factor through the symmetric group action. So there's some compatibility between relabeling the points and swapping the values of X. And then this last condition, the unit condition, says something about when k equals 1 for one of the configurations, there's a unit map on X. So how does this definition fit in with the intuition I mentioned before? Why does this define a homotopy commutative multiplication on X? Let me draw a picture to convince you of that. Well, maybe let me draw a picture for n equals 2. If I have a configuration of 2 points in R2, for example, something like this, that then corresponds to a multiplication on X, going from X cross X to X. And if I want to look at what happens if I multiply in the other order, meaning if I swap the factors of X, this equivariance condition told me that swapping the factors of X and then multiplying is the same thing as swapping the labels of the points. and then multiplying without swapping the factors. So multiplying in the other order corresponds to looking at the multiplication associated with the same configuration, but with the labels swapped. So this lower configuration represents multiplying in the other order. And because this configuration space is connected, I can pick a path going between these two configurations. For example, this one, where I'm just swapping the points, like braiding the points past each other. And every point on this path also determines a multiplication on X. So I get a path between these two orders of multiplying. So this path then gives me a homotopy between the two orders of multiplying. That's what I mean when I say that it has a multiplication that's homotopy commutative. And of course, this picture was for n equals 2. If I look at n equals 3, I still have paths between the two orders of multiplying, but then I have an extra dimension. So I actually get homotopies between homotopies. And if I increase n even further, I get homotopies between homotopies and so on. So increasing n kind of increases this homotopy coherence. Okay, let me end this introduction to EN algebras then by giving you a couple of examples, because these EN algebras actually pop up in a lot of different areas. So the most generic example is an n-fold loop space. So if X is any pointed space, then I can look at the space of pointed maps from an n sphere into X. So here X is pointed. And that is an EN algebra, where EN matches the n in the n-fold loop space. That's sort of the most generic example of an EN algebra. I'll give you some more specific examples. If I look at the space of a disjoint union of classifying spaces of mapping class groups, that's some sort of moduli space of surfaces. So here, gamma G1 is the mapping class group of a genus G surface with one boundary component. And if I take that over all genus, I get an E2 algebra. The last example I'll give you, which will actually come up a little bit later in the talk, is the disjoint union of classifying spaces of general linear groups of a ring R. And this has an E infinity algebra structure. Okay, so that's just a couple of examples you can keep in mind, but there are many examples in many different areas of math. Are there any questions about this definition or anything I've said so far?
What's the multiplication for the last example?
The multiplication for which one?
For the last example, for example.
For the last example, for these, it comes from basically taking block sum of matrices. If I have a K by K matrix and an L by L matrix, and I take the block sum, then I get a K plus L by K plus L matrix, and that gives a multiplication here. And it's commutative kind of up to sign. So that's why you only get homotopy commutativity instead of a literal commutative multiplication.
Okay, thank you.
Sure. Any other questions? Okay. So that's my basic introduction to EN algebras. Now I wanted to talk about operations on the homology of EN algebras. Before I talk about twisted homology, let me say something about ordinary homology. This is a very classical story going back to the 70s or even earlier. So an EN algebra was a space with extra structure, and that extra structure on the space gives rise to extra structure on the homology in the form of homology operations. So whenever I have an EN algebra X, I have the following operations on the homology of X. And here I'm always going to take coefficients in a field. F will always be a field. So the first operation I get is a product. The product basically comes from looking at this map when k is equal to 2, because this space of two configurations of 2 points is connected. And so after passing to homology, I really just get one unique multiplication on the homology of X. So that's my product. There are also a bunch of operations called the Dyer-Lashoff operations or the Dyer-Lashoff-Kudo-Araki operations. These only show up when your field has positive characteristic. And in general, these are really important and really complicated and kind of the main meat of this theory. But in this sort of general talk I'm giving today, I'm not going to go into them. So I wanted to mention them for completeness, but if you don't know what they are, you can just ignore them and know that they exist. Okay, the last operation, which we will talk about more today, is called the Browder bracket. So we have a Browder bracket for En algebras whenever n is finite, so not for E infinity algebras. This behaves a little bit like a Lie bracket, so we sometimes write it with bracket notation. It takes in 2 inputs, say something in homology in degree Q1 and something in homology in degree Q2. And it lands in degree Q1 plus Q2 plus n minus 1. And where this operation comes from is from tensoring with the fundamental class of the space Dn2. So Dn2, that's the space of configurations of 2 points in Rn. And you can show that that's equivariantly homotopy equivalent to an n-1 sphere. So that means in this map we had up here, when k equals 2, if I tensor with the fundamental class of this space, I get a map that raises degree by n-1, coming from the n-1 sphere. And we'll talk about this Browder bracket today, mostly when we're working with E2 algebras. So let me draw a picture for n equals 2. You can think about this as the fundamental class of a circle, but it's also nice to think about it in terms of braids because of the relation to configuration spaces. So as I said before, if I have 2 points in R2, that determines a multiplication. For any 2 points, I can braid them around each other in a full twist. So I get this braid here. That's a path in this configuration space, but it's actually a loop. So it determines a class in H1 of D22. And that's the class that I'm tensoring with to get this map raising degree by 1. So I like to think of this Browder bracket for E2 as like, take your 2 homology classes that you want to bracket together, you put them next to each other, and then you move them around in a full twist. And that's your Browder bracket. Okay, so we have all of these operations on the homology of EM algebras, and they're really useful for studying homology of EN algebras in general, but they're especially useful for computing homology of free EN algebras. I won't define a model for a free EN algebra because it's not so important today, but let me just say that the classical story, which is due to Fred Cohen and Peter May, and their work, they gave a description of the homology of a free EN algebra in terms of these operations that I just described. And it's a very explicit description. So if you give me a space and a basis for its homology, I can write down a basis for the homology of the free EN algebra on that space. So this is really nice for computations. So my work then is to try to generalize this story of operations that I just told you to twisted to homology with twisted coefficients. So I'd like to develop a theory of operations on the homology of EN algebras, but with twisted coefficients. And as part of that work, I would then like to generalize this computation that Cohen and May have done. So I would like to compute the twisted homology of a free EN algebra in terms of these operations. All right, so that's kind of the goal that I've been working on. When n is infinity, this is work that I did in my thesis, and I'm right now working on n equals 2. So this is maybe talking about this actual theory is not so interesting to this crowd. So rather than go into the details of this theory, I wanted to talk about some applications of this work and how it applies to things where maybe you don't care so much about the EN structure, but you can still use the EN structure to find out useful things about the space. Are there questions about this before I move on? Okay, so I'll give you 2 examples of possible applications. The first one is to study homological stability of special linear groups. And I guess in particular, let me say special linear groups of the integers. So before I talk about special linear groups, let's go back to the example of general linear groups that I mentioned before. If I look at the space of classifying spaces of general linear groups, here I'll work with, let me start by working with a general ring R, and later I'll specify to the integers. As I mentioned before, this has an E infinity structure coming from the block sum of matrices. And it turns out that you can use this E infinity structure to study homological stability of the general linear groups. So this was originally due to Søren Gelasius, Alexander Coopers, and Oscar Randall Williams. And actually, they develop a much more general framework for studying homological stability of EN algebras. But in particular, they apply their framework to general linear groups of fields. And they have various different results depending on what field and what coefficients you're working with. Sometimes slope 1 stability or sometimes slope 2/3 stability. These methods have then been used to get further results by Alexander Coopers, Jeremy Miller, and Peter Patst, who have results when R is a wider class of rings that includes the integers, the Gaussian integers, the Eisenstein integers, and some other various examples of R. So they prove slope 1 stability in the case where your coefficients, where 2 is invertible in your coefficients. And then there's some work in progress that's joint with Jeremy Miller and Robin Sroka, where we're generalizing this result of Coopers, Miller, and Patst to a wider class of R. It's a little bit difficult to say concisely. If you know what this means, it's for rings R where the partial basis complex is Cohen-Macaulay. But if you don't know what that means, this includes R that are Euclidean domains or local rings. So just for a larger class of R. So kind of the upshot of all of these results, they all use somewhat similar techniques where you're leveraging this E infinity structure in order to get stability results. But it's really crucial that you have an E infinity structure. Okay, so what about special linear groups? I can look at the same space, the disjoint union of classifying spaces of special linear groups, And you might think that I could try to restrict the E infinity structure for general linear groups to get one for special linear groups. But unfortunately, it doesn't work. You do not get an E infinity structure, at least not in the obvious way. And without that E infinity structure, you cannot use these methods developed by Gelasius, Coopers, Randall, Williams. But it's not too hard to show that the homology of special linear groups is isomorphic to the homology of general linear groups, but with twisted coefficients. So with coefficients in a representation that depends on the units of your ring. And that means we can, instead of studying special linear groups directly, we can study this twisted homology of general linear groups. The right-hand side, because general linear groups has an E infinity structure, this can be studied using the methods of Gelasius, Coopers, Randall, Williams. But there's one ingredient in their method that you're missing here. You need to understand the homology of free E infinity algebras, which was due to Cohen and May. So in this case, because we're working with twisted homology, we instead need to understand the twisted homology of free E infinity algebras in order to carry out this method. So that's where these twisted operations come in. And as I mentioned, this is then in my thesis. This is in my thesis. If R is the integers. There's some restrictions on what coefficient systems I can work with. And so it only works when your units are Z-mod 2, unfortunately. Okay, but given this understanding of twisted homology operations, then you can actually apply this method to study special linear groups. And I should maybe give a disclaimer here that Jeremy Miller and Peter Patst and I have thought about this example of special linear groups a little bit, and we had hoped to get a slope 1 stability result using this method. And after thinking about it a little bit, we think maybe it won't be quite as dramatic as a slope 1 stability result. So this method might not actually be that useful in this particular situation, but this kind of illustrates to you a way in which these twisted homology operations can come up when studying stability. Okay, any questions about that example? All right. In that case, I'll spend the rest of the time focusing on a little bit more in depth on a different example and how that relates to the theory of E2 operations.
So, sorry, I do have a question.
Go ahead.
Can you do the same with the Steinberg group?
With which group?
The Steinberg group.
I'm not sure. I know what the Steinberg module is. I'm not sure if I know it.
Yeah, so it's in some sense it's a covering of SL in some sense.
Ah, okay.
So it's with the universal extension of SL.
Ah, okay. Yes, then you should be.
You do have again. So if you consider the classifying space of the Steinberg group, you will get something which is just above the classifying space of the SLR.
Ah, perfect. Yes, then you should be able to do something similar there.
Okay.
Yeah, exactly. Yeah. I guess depending on how complicated your coefficients are, I might or might not be able to say something about that right now, but maybe at some point soon I'll have more complicated coefficient systems. Good. Yeah, but that's in some case, that's exactly what these twisted operations are good for, is a case where you have something that lies above an E infinity algebra or an EN algebra, but isn't quite EN itself. That's exactly what these are really good for. Okay, any other questions? Okay, then I will go on to talking about mixed braid groups. Let me tell you what I mean by a mixed braid group. I'm going to let BMN denote the braid group that has M red strands and N blue strands, or whatever colors you like. Or another way you could describe this is as the fundamental group of a configuration space, namely the unordered configurations of M red points and N blue points in R2. Okay, so I'll draw you a little picture. You have some number of red points and some number of blue points, and you can have any sort of braid provided the red strands always end up on the left and the blue strands always end up on the right. So I could do something like this. The red strand comes over here and then goes somewhere else on the right. So it doesn't have to be a pure braid, but the red always has to stay on the left eventually and the blue has to come back to the right. So that would be an example of something in B3-2. We are going to look at homology of these mixed braid groups with coefficients in a particular representation, which is defined by the following homomorphism. We'll call it phi mn. It's a homomorphism going from the mixed braid group into the integers mod 2. So in words, what this does is it counts the parity of the total winding number of red points around blue points. Or another way to say this is it's counting the number of crossings in a braid, well, the parity of the number of crossings, but we ignore any crossing of a red strand with a red strand. So that crossing doesn't contribute anything. And we also ignore a blue strand crossing a blue strand. That doesn't contribute anything. The type of crossing that we care about is when a red strand crosses a blue strand. But since the red always has to go on the left, whenever I have a red strand crossing a blue strand, I have a full twist like that. So any full twist like this contributes something non-trivial to my count. So this defines a homomorphism, you can check, and we can use that to define a representation. Given any field F, I'll write F subscript phi mn for the associated BMN representation. So a little bit more explicitly, I mean the group BMN acts on F as multiplication by a sign. So either plus or minus 1, depending on this homomorphism phi. So it's determined by phi mn, whether I have plus 1 or minus 1. All right, so that's some representation, and now it makes sense to consider homology of mixed braid groups with coefficients in this representation F phi mn. Now you might be wondering why we would study this. So this example I was made aware of by Jordan Ellenberg, who explained that understanding homological stability of these mixed braid groups, or maybe secondary stability of these mixed braid groups, has an implication in arithmetic statistics, something related to Legendre symbols. Some of you might be more interested in hearing what that implication is rather than the rest of what I'm about to say, but unfortunately I'm not the right person to explain that connection. Maybe somebody else in the audience knows more about that. But the point is, we're interested in studying these because of some connection to something else. I spelled arithmetic wrong. That's what happens when I talk and write. And I would like to then use EN algebras to study these mixed braid groups. Why is that related? Well, if I look at these homologies, not one at a time, but all at once, I take the direct sum over all m and n. This is isomorphic to the homology of an E2 algebra. And in fact, it's a very nice E2 algebra, namely the free E2 algebra on 2 points, one red point and one blue point. I did not introduce this notation. This bracket notation here, this means a free E2 algebra. And this is homology of the free E2 algebra on 2 points with some twisted coefficients. I'll just write F phi for the system you get by kind of collecting all of these different systems together. So if I had completed my theory of operations for E2 algebras, I would be able to just write down a description of this homology very explicitly in terms of operations applied to these 2 points. That would mean you could just read off whatever stability or secondary stability you were interested in based on that description. So this theory of E2 operations would be really useful for this particular example. As I mentioned, it's still work in progress, so I don't have a complete answer yet, but there are some things I can say about it. So let me take the rest of the talk to say something about what kinds of twisted operations you get for E2 algebras. And I'll say how the general operations apply to this particular example of mixed braid groups. So for the example, let me write X to mean the class of a red point, a single red point. So that's a class in H0 of the braid group with one red strand and no blue strands. And I'll write Y for the class of this blue point, which is in H0 of the braid group with no red strands and one blue strand. And now let me just make a little table where I'll say what kind of operations we get for E2 algebras in general on the left, and then on the right, I'll say how that operation applies to this particular example of the homology of mixed braid groups. So for the particular operations we get in general, we'd like to try to generalize the operations we had classically. That was all the way back at the beginning of the talk. There were all these operations I listed. We had a product, we had the Dyer-Lashoff operations, and we had this bracket that came from kind of putting classes next to each other and then orbiting them around. So the first operation we have here in general is again a product. You can generalize the product to twisted homology, but the product is actually 0 a lot of the time. So for mixed braid groups, that means if I take the product of a class on the mixed braid group BM1N1 with a class on BM2N2, that will be 0 whenever M1N2 plus M2N1 is odd. So in particular, that means if I take the class X, so for example, the product of X with Y is equal to 0. The product of these 2 points is 0. So that in particular means you can see if you stabilize by like adding a red and a blue point, you're multiplying by XY, which is 0. So the stable homology is 0, actually. The next type of operation we had classically was these Dyer-Lashoff operations, which I didn't say anything about. We do still have Dyer-Lashoff operations for twisted homology. They get a bit more complicated. There's sort of 2 types of these operations, twisted ones, which are new, and untwisted ones, which look like the classical Dyer-Lashoff operations. But the reason I didn't want to get into Dyer-Lashoff operations today is because in this particular example of mixed braid groups, we actually have only untwisted Dyer-Lashoff operations, which look exactly like the classical Dyer-Lashoff operations. So there's nothing new here in that regard. Maybe it's not obvious why this implies that we only have untwisted Dirichlet operations, but this is a consequence of the fact that the homology of these mixed braid groups with this particular twisted coefficient system is 0 whenever m and n are both odd. These are the only classes on which we would have twisted operations. And so since these homologies are 0, we don't have to worry about twisted operations here. So the last type of operation we had then was this Browder bracket. And this is where things get really complicated. And this is why this theory is much harder for E2 than for E infinity. So the Browder bracket, let me not write bracket now. So rather than a single Browder bracket in the general theory, we have more complicated operations, which I call Browder operations because they're kind of related to the bracket, but they're more complicated. So instead of just taking 2 inputs, these operations take m inputs, where m can be anything greater or equal to, and they take in homology in degrees q1 up to qm and output something in degrees sum of the qi's plus m minus 1. So just to remind you, for the usual Browder bracket, we had m equals 2, and this was this operation I wrote with bracket notation. So the weird thing here is that you get new operations like this that look like they should be iterated Browder brackets, but that don't decompose into iterated brackets. So the upshot here is that you get a bunch of new operations that are really complicated. Understanding this in general for a general E2 algebra is really difficult. But things are actually a little bit simpler on the right-hand side for these mixed braid groups. So it turns out here you do have a usual bracket defined, and you don't need to consider these weird new Browder operations. You just have the normal binary bracket, but it behaves really weirdly with twisted coefficients. So let me tell you a few things about it to kind of illustrate what's weird now. This bracket is, first of all, not defined on the entire homology. So it's defined on something on Bm1n1 and something in Bm2n2, if and only if m1n2 plus m2n1 is even. So that means I can still take the bracket of x with itself. I can still take the bracket of y with itself. Those are both defined. But the bracket of x with y is not defined. So this operation is only partially defined. And there are also some really weird relations that pop up here. They all seem to come from the following new relation, which gives me a way of rewriting the bracket of x squared with y. So it is allowed to take the bracket of x squared with y. If you're at all familiar with the classical bracket, this bracket can be rewritten using a Leibniz rule because I have a product in one of the arguments that allows me to rewrite this as like x times x bracket with y. But because x bracket y is not defined, I cannot use the usual Leibniz rule here. And instead there's a new relation which says that this is equal to minus x bracketed with itself times y. And this is really strange. Let's see, I still have a couple minutes left so I can tell you why this is really strange. If you think about these two brackets in terms of braids, the left-hand bracket comes from first taking the product of two red points with one another. So taking the product of points is basically just putting them next to each other. So I take two red points, put them next to each other, and then to take the bracket with y, I take a blue point and I move it around those red points. So I end up with the braid that takes a blue strand and wraps it around a red strand, like this. So that's the left-hand side. And for the right-hand side, I take the bracket of X with itself. That's what I get by taking 2 points and orbiting them around each other. So that's a full twist of a red strand around a red strand. And then I multiply with a blue point. So that means I just put a single blue strand next to it. And that's the class we see appearing on the right-hand side. So now if you look at these two braids, it is really weird that this one is equal to minus that one. So this is just meant to illustrate to you that all sorts of really strange things happen with this twisted Browder bracket, even in this simple case where you don't have these weird, more complicated operations showing up. So this is really a very rich theory, but I hope that these three types of operations will again be enough to describe this homology of a free E2 algebra in terms of operations applied to these classes X and Y. Okay, I will stop there. Thank you.
Thank you very much. So any questions in the room or in the chat? I do have one, which did you try to formalize the operations that you need in order to get the results for the stability? So take, for instance, let's say an abstract family of groups, family of groups with a stabilization morphism. You suppose that you have all the operations, and then you try to see what are the properties that you need in order to get, for instance, the stability using the E infinity approach.
You definitely can write down some general things, but it can be a little bit hard to say concretely. So this approach of EN algebras that Galacius, Coopers, Randall Williams develop, they call it cellular EN algebras. So you try to break down an EN algebra and build it out of cells, kind of like you would with a ZW complex. And then based on knowing which cells you need to build your EN algebra, there's like a cell attachment spectral sequence, and you can get a vanishing range there that tells you something about when the homology stabilizes. So to do that, you need some information about which EN cells you need to build your EN algebra. That means if you have a general family of groups, you can make some sort of statement like, if I need cells in these degrees to build my EN algebra, then I get the following stability range. You can make a general statement like that, but it can actually be really difficult given a particular family of groups to see which EN cells you need. So you can make statements like that, but then it's a bit difficult to implement for a particular example.
And you gave several examples at the beginning, but for instance, does it work with the permutation groups, with the stability of the permutation group? So do you recover the stability result of Nakaoka, for instance?
I think that should work. I haven't thought about that one in particular. I think that would work. But of the examples I gave at the beginning, for mapping class groups, there is a paper of Galacius, Coopers, Randall Williams using this method to get secondary stability for mapping class groups. And they, of course, do have the papers for general linear groups. I would think for permutation groups it works. But yeah, I think if you work hard enough with a particular family of groups, you should be able to say something using these methods, but it can be difficult to figure out which EN cells you need.
That's so because, for instance, if you want to get the stability of general linear groups over, let's say, infinite fields or local rings with infinite residue fields, so mainly you just need two properties to hold, and then you get all the machinery on. That's so it's why I was wondering if there are similar ideas with this approach.
Yeah, it's basically, I mean, what we do with all of these general linear groups, for example, is you just show a vanishing range for what's called the E1 homology, which tells you kind of which cells you need, which E1 cells you need, and then from there, kind of the result pops out. So it all boils down to showing a vanishing range for this E1 homology, which is related to the homology of general linear groups with coefficients in the E1 Steinberg module or the split Steinberg module. So really what you need is a vanishing range for homology of general linear groups with coefficients in the Steinberg module, split Steinberg module. And given that input, then you can kind of run the whole argument every time.
Okay, yeah, thank you.
Sure.
Other question? No.
I have a question, sorry.
Yeah.
Can you, I mean, do we have similar results or similar theory for other Barrett groups than the classic one? So for example, for any Coxeter system, do we have the same thing happening?
I didn't quite hear what kind of system, but you were asking about more general Barrett groups?
I mean, the Barrett group associated to a more general system.
Yes, I mean, you should be able to say something about other types of braid groups. You have to be a little bit careful because, for example, pure braid groups are not an E2 algebra. Pure braid groups are sort of like the E2 operad, not an algebra. So you have to look at them in a slightly different way. So depending on how you kind of represent your braid groups, you have to make sure you do actually get an E2 structure. But in general, you should be able to apply this type of theory to kind of a large family of similar examples. Yes.
Okay.
Okay, great. So thank the speaker again.